All right, we are live. Thank you, Kat. All right, so to get us into this, I'm going to give a recap of the celestial theodolite real quick and what we're going to be analyzing specifically when we're going to be going over the differences between terrestrial and astronomical refraction. As of late, there's been some mixing of the two, and it turns out that's actually illegal and you can get a fine from your local government institution. Now, there's no such fine that exists, but I'm writing my local legislation right now to get that changed. We're going to go over some documentation from Andrew Young, who explicitly covers the history of geodetic surveyors and some mathematicians who tried to once merge the two refractive conditions to help ease the terrestrial measurements of the surveying lads, and none of it worked out. And we're going to look at the history of why to determine the validity of one of the explanations that's put forward to try and refute / co-opt the celestial theodolite in terms of it being proof for the globe. So we're going to break that down explicitly. So we're all familiar with the basic concept of the celestial theodolite, but a quick recap here is suppose we have an eastwardly peak here, and the stars are going to recede into that peak. And when they recede into it, we're going to note the time in which they were no longer visible. Then we're going to hop into Stellarium or our favorite astronomy software, and we're going to enter the coordinates for the peak that did the occluding. And we're going to look at we're going to reference the true position of the star at that time. And the reason for that is we're considering that to be the light source of the star that we actually see, because we always see the apparent position due to refractive conditions and the motion between us and the star. So the star being in motion relative to us, we always see what you can consider the after image of. That star that you see isn't the true star, it's the apparent image that you see. And to kind of illustrate that, we have Taylor here with a cup of water, a knife, and a laser. Now what we're going to see is the effects of refraction, refracted light, and a refracted image in real time, because part of the globular explanation put forward is that the terrestrial, that a combination of terrestrial and astronomical refraction lifts the starlight up such that it intersects at the apparent angle for the globe if you were to measure the mountain peak, accounting for terrestrial refraction and globe drop. So it would drop due to globe, but it would also be lifted up a hair due to terrestrial refraction. So we'll see what this looks like as Taylor moves this laser beam in such a way that it intersects with the light, or I'm sorry, that it intersects with the knife here. And what we're looking at is, you see how this dot remains in the refracted image of the laser beam. It's directly, on par with where you would see like the physical object. So you see it's refracted through there because the water on the other side is bending the light as it's traveling through the cup to the knife, and it's bending it over around. So we're seeing this after image in the light projected inside of it. So the conclusion we can draw from this is that a refracted image does not occlude refracted light. In order for this light to disappear, the physical intersection of this laser that Taylor's holding has to cross some threshold of the physical object of the knife that's in between us and the laser. So let's see how this plays out as she moves her hand back and forth, adjusting the angle of incidence between the true object and the refracted image. Oh, cool. It's doing the thing where it's playing, but it's not actually playing. Nice. Okay, there we go. All right, so you see there when she moves her hand further to the left there, the light actually disappears inside of the cup. Now, it obviously wasn't due to the refracted image over here. It happened when the angle of incidence intersected with the physical object. And that is what creates the actual occlusion. So that's the premise that we're going to be working with, and that's why we go to the mountain peak to determine the cause of the occlusion, because the angle in which that star resides is going to give us a mutually exclusive outcome based off of either drop over distance or no drop over distance. So we have gooses set up here kind of illustrating the same thing. And I like this a lot because we can actually see here the separation difference. So when there's no medium between this dial and the observer dial here, the light gets obstructed basically when it intersects 1-to-1 right here with the mountain peak, or with the dial. And then when you add, and you can line up a stick here between the Dow and the occlusion Dow. And this is similar to how we draw a tangent to where the star once was to make our triangle. So this is very similar to that concept. So as we can see here, at the time of occlusion, the light source is pretty much in alignment right there. It's a little off, but it's, that's where it's at. Now, when we add a refractive medium between the light source and the peak, and also the observer here, what we're going to find is that the light source has to move further away from the Dow before it's actually physically intersected enough so that the refracted light coming through this part of the medium doesn't get bent around for the observer over here. So so we're going to quantify this separation here by subtracting the known position of the true position of the star at the time of occlusion minus the rise over run of the mountain peak with no drop over distance. And the reason we do no drop over distance is because the angle of occlusion it's nowhere near the globe. So there's no reason to do the drop over distance one if it's not even close. But, and we'll get into how much astronomical refraction they predict and how that affects everything. But what we're doing here is just comparing how much lower it had to get, essentially, how much with that change in elevation difference before it was actually occluded. So that's the basic backbone of occlusions of what we're going to be looking at here. All right. So any questions so far about occlusions and refraction? If not, we'll go ahead and proceed on with a crash course of the review. So in terms of light propagation, is light a photon and is it a wave? Doesn't matter how you want to conceptualize it for the purposes of this analysis, but for the ease of use, we're going to look at it as a wave. But if you want to know about the history of undulatory theory and emission theory, there will be a recap provided at a later time. But we've been through it before, but for the purposes here, pick your flavor, doesn't matter. Quick recap of Snell's law. So when there's no refractive medium between us and the drain at the bottom of this sink, we can't see the drain here from this angle. When we start to fill the sink with water, it's filled with a refractive medium that's going to bend the light as it leaves the medium there to come to, when it leaves the denser medium of water and then goes into air, there's going to be a change in the angle of incidence there per Snell's law. So what we can see here is that the drain gets lifted up now. And to see kind of what that looks like, this is the path of light being altered by the change in the refractive medium. Very cool stuff, basic principles for how refraction works. Now we're going to look at the angle in which starlight comes in to intersect with our eye, and that's going to be extremely important because the conditions that affect terrestrial refraction are all dictated by temperature changes in what's called the boundary layer. And what we're going to see is that the incoming starlight is nowhere near the boundary layer. And we've got several measurements that kind of quantify the position that astronomical refraction is a different phenomenon from terrestrial refraction, and they do not, mixing them is completely improper. So here we have the starlight coming down through the atmosphere, bending down, and refraction causes it to bend up a little bit. So the real position of the star would be here, sending light into your eye there, hits the refractive medium of air, it gets bent up, and it looks like it's over here now. Or, it looks like it's above the source. Ooh, it's showing the long distance travel from which it comes. And then once it enters that vacuum, you see the angle of incidence starts to change right here as the gradient changes. So it's coming in on this geodesic, which is not to be confused with a straight line, but it looks super straight. Yeah, it's coming in on a curved linear path. And then it hits the atmosphere and it goes curved linear again, but for realsies this time. Yep, at some point this happens. All right, now another diagram here, just kind of illustrating the same thing. Source below, refraction causes the image to be lifted up. Now, when we look at the typical refraction corrections that are given for angles that are 20 degrees and above to your zenith, you can use a simple formula of R equals 57 over the tangent of your angle. 57 being just some coefficient that they added, and that basically normalizes, it basically gives you like an estimate for the refractive conditions to move the star to where it needs to be to follow the 15 degree per hours that you're going to be using to sight it, to map it to a ground position. and find your location with a circle of equal altitude. So all of this is determining how much the star is supposed to move from its true position to make it so that it aligns with where it's supposed to be on the two-sphere model. And the sphere that it's supposed to be referencing would be the terrestrial sphere. So they're supposed to have their lines matching there. Now, when you get 20 degrees or below the horizon, there's different formula that are introduced that provide empirically derived coefficients that you tag on to the formula that adjust the angle amount that it's supposed to drop. So in this, you'll notice when you try to do like a rise over run, that's getting an elevation, right? Or that's giving you an angle that's based off of like a vertical elevation. Well, on the inverse there, the cotangent would be like lifting up that triangle. So if you're going to apply a cotangent to a tangent, you could think of the tangent as being like, okay, how much does this converge at the horizon? And then the cotangent would be like, okay, how much do I have to lift you at the horizon based on your angle so that you don't converge to zero? And the output to make real world observations fit the expected model for the two-sphere model, they output this number here, 10.3 and 5.5. So you put these in conjunction with your alpha. Your alpha is just going to be your raw angle. So whatever your raw angle is, you're going to put that in with this formula. And these are temperature and pressure conversions for Celsius and whatnot. So you enter your temperature and pressure. Now, this gives the appearance that it's accounting for real variables, but your local terrestrial temperature and pressure has nothing to do with astronomical refraction and doesn't impact this in any sort of meaningful way. But what does happen here is that this is driven, like the whole formula correction is driven by these two coefficients here that have nothing to do with any actual temperature gradient or pressure gradient or density of air or air mass or anything like that. It's just a number that it's basically a number that has to be because they know it's a globe, and the only way that this could be mechanistically facilitated is if there's a refractive gradient for some reason that's producing this. And we'll get into how they produce the output of these, how they model it out to even get these kind of numbers to put in here to this, which is going to be based on an unsubstantiated claim, as we're going to find out here as we continue. But that is the significance of how they keep the model in alignment when things at the horizon do not obey the 69 or the 15 degree per hour movement, which facilitates the 60 nautical miles per degree, which is required for the movement of the position of the stars if you think you live on a globe, and that the change in the position of the stars is due to the geometry of the Earth. All right, so I went over all the refraction stuff. Okay, so we're gonna, what I covered earlier in regards to taking the difference of the true position of the star with respect to the true elevation of the peak relative to the observer, that's going to allow us to introduce some new metrics. So we're going to have the delta astro refraction. That's going to be equal to the astronomical refraction that's measured minus the predicted amount that's given to us by the empirically derived formula. And that's going to equal the true amount. Now, I changed the annotation a little bit as we go down, but the basic premise here is that we're going to be able to compare and contrast how much refraction there actually was versus how much they actually predicted. And because we're using trigonometric functions, all based on the same angles and relative distances, we can actually turn those angles into an elevation amount. So we can look at it in terms of how much did this change in terms of meters to make it kind of easier to understand, because 11, like something small, like 2 arc minutes doesn't sound like a big difference. But when we see how it applies relative to the ratio of the triangle that it would make in the instance that we're doing the analysis on, you can see how this is a huge, this is what this means. So it'll give us a clearer picture as we continue our analysis, so we can kind of determine the validity of the amount of astronomical refraction to see if the computational models actually represent reality or if they represent a security net for the model in which they are correcting for to support. Okay, so the basic premise here, the stars move at 15 degrees per hour or 15 arc minutes per minute. Astronomical refraction at the horizon is around 25 arc minutes, depending on the angle. So when you get anywhere from 2 to sub 2 degrees, the refraction goes from anywhere from 12 to 28 arc minutes. I've seen. So when the star gets low at the horizon, it causes it to linger, which throws off the 15 degree per hour scale, because if the star is following 15 degrees per hour, when it gets to the horizon, it's going to be occluded by the Earth and it should no longer be visible. But for some reason, it's still visible. So this is the explanation that they've put forward. All right, and then here we just have different positions of the star as it moves, kind of noting the angles that will facilitate different refraction corrections. So if a star is at your zenith, you're going to experience the least amount of refraction. You'll probably experience between 2 to 3 arc seconds of refraction, which is probably the lowest you can get. I have a quote from Sky and Telescope magazine where they're talking about as much. And then when you get off into like the 40, 60 degree range, you'll probably get like an arc minute, or almost an arc minute in corrections for the for angles like that. And then as you get closer down here to the horizon, these two, now this isn't to scale obviously, but as you get down here to the horizon between 2 1 degree, sub 1 degree, etc., that's where you're going to get these larger corrections that are in the tune of 18, 20 arc minutes, etc. Okay, so there's a notation guide here provided. So if anyone wants to reference that, all of that is of course provided, and then it'll be on the Obsidian page as well. But if you want to interpret the diagrams put forward to get like exact definitions for what these things represent, everything is here. So just the basics: geopeak, the physical elevation of the peak with no drop over distance; the geopeak drop over distance for the peak, accounting for curvature; apparent globe peak, this is the apparent angle to the peak, accounting for terrestrial refraction. And so adding terrestrial refraction to the globe drop angle. And then we have the apparent star with respect to the observer's location, the apparent, and the true star's position with respect to the observer's location, and the same for the mountain peak. So star peak apparent is apparent with respect to the peak, and true, same. And then we have star geo observed prediction, and this is going to be the prediction for the true position of the star for the observer using the formula 360 times the distance over 2 pi r. And this holds pretty good, pretty close. So we'll take a look at that as we go through. And then we have the notation for astronomical refraction given to us by Bennett, and that's the formula that produces the 20 arc minute, etc., for all these different angles. We have astro refraction measured. That's going to be the actual separation between the true position and the peak. And then the refraction over compensation is going to be the prescribed amount by the Bennett formula minus the measured amount. And that's going to tell us how much they overcompensated by. And again, we can ratio that into meters and see how that affected the meters in terms of, the drop over distance. Because if I said, hey, there's 200 meters of drop over distance here, but you accounted for 12 arc minutes of refraction, are you going to immediately understand that 12 arc minutes of refraction is exactly 200 meters, that it 1-to-1 compensated from it? It makes it seem like it didn't, that there's some ambiguity to it. So that's the purpose of converting those to show exactly how it influenced the measurement. And we got our tangent functions here, which gives us a unit measurement, or a unit number. And then so that'll be like what we would use in meters. So when we're converting things from an angle to get what it would be in meters, this is the function we use. And then we have the inverse of that, which is the arctan, which gives us the angle based on the unit numbers. So if we use meters, we use 2 metes together, we're going to get an angle. If we use an angle and a meter together, we're going to get a meter, or a unit number. Then we have 180 times the distance over 2 pi r, which is just creating a central angle to a sphere of a radius of r. So this is how the globularist would relate the drop over distance to the peak. So when we calculate how much drop over distance there's going to be between us and the peak, we use 180 times the distance over 2 pi r. That gives us an angular amount. We convert the angular amount using a tangent function, and then we see how that aligns with drop over distance. And then we have 360 times the distance, which we went over. Same thing as the first, but it's just completing the full circle. So we get the extra drop there to figure out how much to subtract to put on to see where the star is going to be. And we'll see how that plays out as we continue. Now we have, now another thing to go over real quick is that the true position or geometric position is the reference to the star's position with respect to where it was on the first point of Aries. And the first point of Aries is the night of the vernal equinox, which is where it's like a snapshot of the stars, where they're at and how they relate to positions on the ground at that time. And then they relate time to, what's it called? Greenwich Mean Time. So anyway, there's nothing like mutually exclusive about this. This is just a snapshot of where the star is, and then you add 15 degrees per hour to it. That will always tell you where the true position is. That's how you calculate that. That's how it's derived. We just use our favorite astronomy software to do it because it does it automatically for us. But if you wanted to, you could get out your almanacs and do it all by hand for funsies. but we're going to go ahead and take a pass on that. Okay, now we've been encountering this argument for the past. See, this diagram was first made in March. Now we've put forward refutations to it and whatnot, but the way that it's continually presented as if no explanation has ever been done, well, now we're going to give a full treatment to it and analyze it to completion. So yesterday, I read off what I'm going to go over here now, and John said that this was a accurate representation of his position. And it's not necessarily just his position. This would be like the only tenable position for the globe based on the principles of how they understand refraction in terms of it lifting up things one to one, like how they claim for terrestrial refraction. And we'll get into the effects of how that's possible and what that means and whatnot, and how untenable the position is that's put forward for the globe explanation. So here we have this diagram that the most important thing on this diagram that I want you guys to take away from this is it says right here, the place that the physical occlusion happens, and we have a line going right here to the mountain peak. This is why we go to the mountain peak. You often hear things like, why are you moving the observer to where he isn't? Aren't you over here? Yeah, you're over here, but you didn't occlude the star. So in order to determine the angle that occluded the star, we have to go to the peak and reference where its true position was with respect to that peak. And if it's at the same angle that we would have calculated for the relative angle to the peak here from our position, then we could draw a nice little tangent that goes all the way to the star like we do here. So this pink line here. You kind of are at that point because that's your crosshair of your reality. So like you kind of in effect are at the peak. But it is self have method in a way, I guess. Essentially, because that's where that's where we used to have an image where there was a lad here at the observer location, and he had a giant telescope that extended to the mountain peak that just rested on it. So it's like, yeah, same exact concept. So it's just if the angle that you predict for rise over run is the same or thereabouts when the star gets occluded with the true position, then that is going to tell you, okay, that was the physical intersection point. Now, the two angles predicted for globe and flat Earth are not the same. So based off of that angle where it gets occluded, that's going to tell us, which one of these models is more likely correct. Because we can convert the drop over distance into an angle, subtract it from our angle, and figure out which angle is the one that matches the position of the star at the time of occlusion. So what John puts forward basically is that from the observer location, if you hop into Stellarium, you'll see that the star is at 2 degrees and 5 arc minutes. But it's being refracted up by 12 arc minutes. And that refraction is lifting it up just high enough to equal 219. Oh, I'm sorry. That also, he also adds on, because he's 2 arc minutes off of 219. So then he adds terrestrial refraction into it to account for that. And that makes it 219. So accounting for astronomical and terrestrial refraction, he lifts the star the star is able to be lifted to the peak here where it intersects at 219, which is the predicted refracted apparent angle for the globe at this time. Very cool. Seems like he's on the right track there. So that's his exact position. So I'll kind of read through here so we can understand it. So terrestrial. So to understand John's argument, to understand this diagram and even our diagram or even our argument, it's necessary to break it up into two components. So first, we're going to go over the terrestrial. The argument made by the globularist is that referring to the star's apparent position with respect to the observer, the occlusion is predicted at 219. This angle closely aligns to the globe peak apparent angle with accounting for terrestrial refraction, which is looming, and that makes it 219. Okay, so, and then remember that the occlusion happens at the physical location where this happens. Celestial, the celestial component where the starlight's coming in from is now taken into consideration. From the observer's location at the time of occlusion, the geometric location of the star is given by 360 times the distance over 2 pi r, producing an angle of 2 degrees and 6 arc minutes, which the astronomic refraction from Bennett makes it 217, and then they add the 2, for the terrestrial refraction, giving it 219. So terrestrial angle is 219. The celestial angle, with adding the terrestrial, comes out to be 219. So it must logically follow that the intersection occurred thereabouts at 217 and is viewed by the observer around 219 due to astronomical and terrestrial refraction, the conditions only possible if the Earth were truly a sphere. So the primary argument is that this method is simpler because you only have to go to where the observer's at. You don't have to do anything like referencing where the peak's at. For some reason, it's like taboo to reference where the peak's at, even though the purpose of it is to determine the occlusion with respect to that, so that you can actually know for sure if any of this part of it is true, because we need to know what happened on the other side of the mountain to determine if this hypothesis is correct or not, right? So just looking at it from the observer position tells us nothing unique or independent. So we put it all together now. So a globularist proponent would argue that this is no coincidence, asserting that the two angles match because the Earth is a sphere. The predicted elevation with the refraction matches the apparent position of the star at the time of occlusion. So therefore, the Earth is a globe. Now, this logically follows that if the star is sub 11 arc minutes below the peak, it's still being refracted above the peak 1-to-1. And once the entire 12 arc minutes is eaten up, putting the star at 2 degrees, putting the true position of the star at 2 degrees, 5 arc minutes, the star will no longer be visible. And that's where it gets visually occluded for the observer 50,700 meters away. Therefore, Earth must be ball, right? Pretty straightforward, seems pretty foolproof. But when we get into the mechanisms of terrestrial and astronomical refraction, which we're about to do, we're going to see that the position of adding the 2 arc minutes of refraction to lift it up to meet the physical, to overcome the physical elevation of the peak to match the terrestrial refracted image is not a tenable position at all. And what they would actually predict differs from what we actually observe, because if the refraction looming effect occurs in the same respect that how they say a star is below the horizon, but it's being lifted up by refraction, they would have to say that when a star gets occluded by a mountain peak, it wouldn't, like, just try and imagine this. There's a mountain peak off in the distance. You see a star setting into it. Instead of the star instantly vanishing when it intersects with the peak, the star just lingers there. That's what they were predicting. The audience can't be heard on YouTube. We hear cats opening. It sounds like the volume is very low. JT, are you there? Hang on, yeah, audio check. Can you guys hear Shane? Say something real quick. I'll just look at my OBS. I can tell right away. Oh, nope. No. Yes. I'll tell you what happened. It's not necessarily a Linux. Speak again.
You got it? Now you can hear it, I bet. I bet you just plugged in the Windows adapter and now it's all good. That's probably what happened.
Yeah, I actually just called Bill Gates and I was like, yo, bro, I'm having a problem. And he just hooked me up. So
a couple sniffs and we're in. All right,
cool. So, but everybody could hear me through that whole thing, right?
Yeah.
All right, cool. Can't hear the audience. Also didn't hear Cat's opening. Oh, okay, that makes sense. They didn't hear Cat. That makes sense. All right, Cat, give us an intro real quick on the fly. Mid-prezi. Send it.
Welcome, lads and ladettes, to Aether Roundtable number 100. In the middle of a review of astronomical and terrestrial refraction.
Thank you. She's a real future here.
That's awesome. Thank you very much. We'll put that in post-processing. There's no post-processing around here. It's in permanently now. This has now been canonized. We do intros in the middle now. All right. So moving on here, we put everything together and now we're going to look at the mechanisms of terrestrial and celestial refraction. So we already went over how astronomical refraction affects the measurements by lifting it. So in immediate contention, I would bring to the globularist proponent's argument is that 219 is the elevation that's necessary for all that to transpire on a sphere, and that the refracted amount of the peak of 2 arc minutes did not physically occlude the star, so it can't be considered in the analysis if the star's position is at 219 to be refracted. So therefore, the standard refraction is not considered when analyzing the physical intersection of celestial bodies with the terrestrial, a choice that will be quantified later as the difference in angular position between the peak and the true position of the star has been lower than the amount of terrestrial refraction at the observer's location, and it had no impact on the measurement. So that's shout out to Mount Rosa there. Because the true position is 2 degrees and 6 arc minutes, the given match of 219 by way of refraction from Bennett dictates that the physical elevation must be 217 and must be otherwise the starlight has no chance of overcoming the 219, as there is only 12 arc minutes of celestial astronomical refraction, and the star is already at 217. Lifting the star another 2 arc minutes to match the optical globe prediction for drop over distance is improper. And we can see a bunch of citations from Andrew Young here, which I'm going to go over as we continue here. And when we analyze Mount Rosa, we show that the standard refraction has no meaningful impact on the occlusion timings. A quick recap from Andrew Young reminds us that terrestrial and astronomical refraction, while having the same effect, is mechanistically different, leading to a different magnitude and effect. Terrestrial refraction, the path of light experiences a constant angular displacement for all parts of a vertical target because of a constant lapse rate. So as you increase in altitude above the ground, the temperature is going to be kind of uniform, causing an object to be like lifted uniformly. So if you've ever wondered how they describe how refraction lifts something like a vertical object 1-to-1, where you can kind of see like the base of it. Well, it's because of the gradient in which they're describing leaving the horizon is essentially linear, so it lifts it up kind of 1-to-1. Now, obviously, they invoke an insane amount and yada yada, but I'm just saying, like, mechanistically here, this is what's happening, and this is how it's affected. So the light from the sun comes in, heats up the ground. That temperature change is most affected by things that are low to the ground, the terrestrial objects, right? Because that's where the gradient of heat transfer is the most, and that's where we get the most impact of changes. So if you've ever seen something like Skunk Bay, and the positions of everything changes all throughout the day, all of that is due to temperature changes in what's called the boundary layer. The boundary layer is that surface of air that's closest to the ground that allows that thermal heat transfer to transpire. That changes the gradient, that causes the refractive changes that we see throughout the day. Very cool stuff, but it is dependent on that boundary layer interaction. And what we find is that astronomical, starlight basically comes in at an angle that never touches the boundary layer. It has no interaction with it. And the boundary layer, as you get higher in altitude, dissipates. So its ability to affect things at altitude is, gets diminished. So it has so conditions on the ground actually have no relation to what's going on in the sky, and cannot be represented radially outward from a sphere using a static model to create a smooth gradient.
That makes a lot of sense, actually.
Yeah. Yeah. Well, but just wait. Insert Laplace's theorem. What do you guys think he does? Introduces a proportionality ratio to air mass so that he can say that the density at the time is the same density of air mass at the horizon, so that they could use a smooth gradient model that's calculated spherically outward, so that they could produce these coefficients that are applied at angles to the horizon to lift it up.
And they're right back in. Okay.
And we're back. Yeah, so that's Laplace's theorem right there. So he has. Yeah, go ahead.
So you started by saying that the 2 arc minutes of terrestrial refraction for our Pikes Peak example wouldn't be mechanistically necessary to add. Why is that, though?
It's not that it's not that it's necessary. It's that it's completely not. It doesn't affect the light. So think about it like this. Let's say, to keep it simple, let's say we have a flat baseline, and then we have, let's go 10 meters above that. So 10 meters above that, the air density and all that is transferring heat, and all that is affecting the temperature, pressure, density, all of that, right? So, but only within that 10 meter span. Now, as we go to 20 meters, the effects from that 10 meters dissipates to it halves essentially, right? And then let's go to 30 meters. Now it's a quarter. Now let's do 40 meters. Now it's basically zero, right? So 50 meters. Now it's even more zero. Now we're at 60. Now something else entirely has to happen, because these two aren't even related anymore, and the heat transfer isn't doing any, mechanistically it's not there. So there's no relation to the two. So when the starlight comes in at an angle from the top like that, from outside of the boundary layer, it's not getting any terrestrial refraction effects, any of that.
Right. So
yeah.
So I get that it's not affecting the star, but aren't they arguing that they're applying terrestrial refraction from the observer to the mountain, specifically to the peak? They're
If
saying
it-
that the peak
yeah.
itself is refracted by 2 arc minutes.
Yeah, so if it hits the peak's true elevation at 217, then that's when it would get occluded. So
Okay.
so
Right.
so it can't be occluded at 217 and then lifted up by 2 arc minutes by an effect that has no relation to it.
And didn't we just say that we didn't want to apply a uniform radially outward on a sphere at a constant uniform rate, but isn't 2 arc minutes calculated from 7/6R dispersed at a per kilometer basis to 2.4 arc seconds per kilometer, and then actually dispersed at that uniform rate across the 50.7 kilometers to get the 2 arc minutes in the first place?
That's exactly what it is. We don't do that, but they do.
And that's mechanically unsound. Okay. All right.
Yes,
Just follow.
yes, and that is mechanistically unsound. You cannot do that. They have no relation to one another. And then actually, yeah, even Andrew Young, after laying out Laplace's theorem and the proportionality thing, he's like, hey, the biggest weakness of this assumption is that there's no grounds for it. You're just assuming that the density is proportional to the air mass at your line of sight. There's
It
no
needs to be.
because otherwise, yeah, if it's not, then if it's not proportional, then there's going to be a change. They need a smooth gradient model, or like they need a smooth model to facilitate like the to curve fit, right? They can't do it dynamically because then they'll get different values at the angles. They need a smooth gradient. So the big weakness of this is ends up being what's actually wrong with it, why it doesn't work at all. And we're gonna quantify the amount of actual astronomical refraction in these measurements, and it's not even close to what they predict with this proportional air mass ratio. When I was going through all the history of the different formulas and the different things that they do to check the formulas and all the math they do, it's all modeled out off of this assumption right here that the air mass proportionality ratio. It all starts with this, and then they project radially outward from a sphere of 3959 all the way out to 20,000 kilometers above the surface. All right. All right. So we went pretty heavy on the boundary layer stuff. I think we're good on that. Okay. Okay, so to find out if the globularist hypothesis is correct about the terrestrial hybrid refraction with astronomical, to see if it lifts it up 1-to-1 like they say they do, we can analyze using the position with respect to the peak and see what the differences are. Because if they match, then what that would mean is that the star would have to be lingering there until the true position gets down to 206 with respect to the peak, which would change the occlusion time. And the occlusion time matched it's the same time for everyone. So that didn't happen. So we can rule that one out. And now we're just
What
going to.
do you mean by 1-to-1? Sorry, just so I understand. Lifting such a body 1-for-1. What does that mean?
Okay, so if the star's true position is at 2 degrees and 6 arc minutes, and so it's below the peak by 12 arc minutes, and they say, hey, there's actually 12 arc minutes of refraction, and that's lifting it up to 217. So in other words, there's 12 arc minutes of refraction allowing that star to be below it. And that's explaining why at 205, it's still above the peak. Make sense?
No. What do you sorry, what do you mean 1-for-1? Like
so there's 12 arc minutes of refraction. This means that the star has to get 12 arc minutes below the peak before it's not visible anymore.
Right.
Okay, that's 1-to-1. What we're going to find is that it doesn't have to go 12 arc minutes below the peak. It only goes 2 to 4.
They needed to do that. Okay.
Yeah,
okay.
they need the 1-to-1 ratio because they're asserting it's being lifted up by the difference in the true position to intersect with the peak, and then the terrestrial refraction takes care of the rest. That's what they hinge their whole position on. All right. And okay, so specifically, let's see, where were we at here? Going over the refraction amount. So to see if that hypothesis is true or not, whether it can lift it up 1 to 1, we need to reference the position at the peak, do a little subtraction, and from there we can determine which is correct. All right, so now we're going to get into the actual analysis now that we've gone over what they predict and why, and we've went over mechanistically what we predict and why, and how their position isn't tenable, but we'll continue the analysis anyways, just to really seal the deal and quantify the effects of refraction. So to start us off with Pikes Peak, now keep in mind, they've said that for every measurement that we've done, it's compatible with the globe based on the apparent positions of the stars. Just using the apparent with this terrestrial refraction combination. That's how they're hanging in there. This is their lifeboat. So rise over run to the peak for Pikes Peak at a distance of 57,000 and an elevation difference of 2027. We get 2 degrees, 31 arc minutes. For the drop over distance, we get 13.5 arc minutes, which with subtracting that from the true elevation, gives us 2 degrees and 17 arc minutes for the globe. So this is the physical elevation that they predict. This is what we predict, 217. So the apparent globe angle here is when they add in the terrestrial refraction, which is 7/6R converted into degrees per meter. And this is what it comes out to. For this case, it comes out to be a little under 2 arc minutes. But when you total it out, it comes out to be 219 there. It comes out to as if it were 2. Now we have the apparent position of the star for the observer's location is at 219, so it closely matches what they would predict for the apparent position. Very nice. And we have the prediction for the drop over distance to the star's true position, which is given by 360 times the distance, which gives us 27 arc minutes. That's double the amount of the drop to the peak. And when we subtract that from the rise over run to the peak, we get 206, which gives us the true position of the star. And that actually matched as well. Very cool. Now we have astronomical refraction given to us by the Bennett formula for an angle of 2 degrees, 31 arc minutes above the horizon. He prescribes 13 arc minutes of astronomical refraction, not to be confused with terrestrial refraction. Now we have the flat Earth prediction. Rise over run to the peak gives us 231. The star's true position with respect to the peak was at 233. The prescribed refraction per Bennett is 2 degrees 45 arc minutes, 13 arc minute refraction. Now they have an actual measured difference here. So when we compare the intersection that occurred, it would have been minus 2 degrees minus 2 arc minutes from our prediction, because we predicted lower. It occluded a little higher. So we'll see what that, why that was here in a second. And then this gives a difference. When we subtract the -2 from the 13 predicted, we get 15. So we'll see how this affects the measurements now. Okay, so to give a little description here of the math before we get into it, I was kind of justifying the 180 times the distance to show the equivalence here. So if you get the drop over distance between the peak, just to verify that we're not doing anything weird, you can do the square root of the radius squared plus distance squared minus the radius, and that will give you the drop over distance to the peak. And we can compare that to what the 360 times the distance formula gives, and they're the same every time, so it all works out. And then we can convert that angular amount to drop over distance, and it gives the same amount of 200 meters of drop over distance for the peak at that location. So we're solid on our mathematical interpretation there. So just a little context on the equivalence between the two, because there was like months ago, it was like, are you guys even calculating the globe correctly? We went through a whole thing of that, and now everyone's in agreement that we were doing it right the whole time.
Well, yeah, all 5 proposed methods came out with 201 meters, but each time it was wrong until they all agreed that it was 201. So now we have 5 different metrics to calculate 201 meters of drop.
Dude, we were simultaneously doing it wrong, but via the interpretation of adding 2 arc minutes of terrestrial refraction, which to even get down to that angle, they had to use the same math that gives us the angles that we're getting to apply their amount, and then it was okay, while we're also simultaneously wrong and strawmanning the globe mathematically. Very cool. All right. Okay, so now we're going to compare these two and look at the figures. So the amount of astronomical refraction was 13 arc minutes. Convert that into meters. It's a 186 meter lift. The amount of drop over distance to the peak was 200 meters. So now there's a 14-meter difference here instead of 200 meters between the peak and the observer. So now we're, now who can tell, right? Optically anyway. And then the measured difference here came out to be minus 2 arc minutes, and that converts into minus 29 meters. And that refraction over compensation difference, when we add the two together or subtract the two, we get 216 meters in actual overcompensation for what they predicted. So they completely overshadowed the amount of drop over distance. But in this scenario, what we notice is that the actual measured refraction amount doesn't exceed the amount of drop over distance. And this is going to be an important metric to understand, because there's going to be instances where the amount of actual refraction matches or doubles or triples the amount of expected drop over distance. And in these instances, that constitutes an invalid measurement, because the refraction conditions at the measurement make it such that you can't determine whether or not the Earth is flat or a globe there, because the refraction conditions entirely facilitated the measurement. It wasn't like a natural measurement of the globe. It's only facilitated by specific conditions, which we'll go over as we get to those measurements. But keep this in the back of your mind, that if the refracted astronomical amount is larger or the same amount as the drop over distance, invalid. All right, the true refraction. Okay, yeah. So the true refraction conditions at the time do not exceed the expected drop over distance. This qualifies as a valid measurement. The prediction is off by 2 arc minutes. Oh yeah, so their apparent position is now off by 2 arc minutes. So remember how they were like, hey, if we have 2 arc minutes, it's actually explainable just as is right here. Well, now that we've established that terrestrial refraction plays no role in lifting up the starlight on the other side to give that appearance, that it gets occluded at 219 for the angle over here, then they become off by 2 arc minutes. And this is going to be a trend that continues for a large majority of the measurements. In a couple instances, they end up being above, which, wasn't measured because the star occluded. So that's, untenable. So as we move on to Blodgett Peak now, we have rise over run giving us 1 degree, 16 arc minutes. With drop over distance, they predict 1 degree, 6 arc minutes. Terrestrial refraction, they predict 108. And the star was visually at 109 at the time of occlusion, pretty close. So let's see what happened with respect to the actual occlusion. So at the peak, the star was at 1 degree, 11 arc minutes for its physical intersection. And that gives a difference of 4 arc minutes from their predicted celestial refraction amount of 17 arc minutes. So we have a difference of 12 in the overcompensation there created by their refraction coefficient. So when we analyze that, we have a drop over distance to the peak of 101 meters. We have an overcompensation of 131 meters, and we have a measured amount of 49 meters. And we were off by, the other thing to note here is when we see this number here, the astronomical refraction measured, this 4 arc minute difference, this amount is actually how much we're off on the prediction. Because remember, we predicted 231, but it occluded at 233, and we ended up getting this negative amount now because it's higher than what we predicted. How did it get higher? Actual astronomical refraction corrections. Because when we convert this 2 degree separation into meters, it's 29 meters. Essentially 30.
Whoa, look at that. So that makes it almost perfect.
It's 30 meters. And then so we were off by 30 meters when we derived the elevation. And you derive the elevation based off of the tangent of the distance to the occlusion angle. So the only thing these share is the occlusion angle.
That's amazing. So all the time they were shouting astral reflection, and we should have been shouting that to make our new J factor to apply all of our predictions to perfection. Interesting.
Oh, sorry. They do share the distance as well. So they share distance and occlusion time. So those two factors, right? The factors that, are dictated by the rise over run prediction, Now we see like, okay, well, now we're off by a little bit. And this is the amount of actual refraction is y. It directly relates to our angle. And then we can actually use that later to see why we're going to be off on some of the measurements where the actual refraction amount is, that lingering amount is changing the distance and elevations that we predict, or that we derive off of those angles, because it's lifted it up higher than considerably higher than what we predict. And as the angles get smaller, the effects and the change in that ratio becomes greater. So, as we go through this, we're going to see how this impacts the measurements to an insane degree. It's awesome. All right. Okay, so that was for Blodgett Peak. So again, here we had that same relationship. We were off by 49 on our elevation derivation, but that was because the star was lifted up. It had to get 4 arc minutes lower than the peak before it was occluded. Okay, so it constitutes as a real measurement because the drop over distance doesn't exceed the actual refraction amount. And now they're off by 3 arc minutes because they don't have their terrestrial refraction there to help them overcome. Cheyenne Mountain, the rise over run gives us a degree 0.5, and then we have 11 minutes in drop over distance, giving us 53 arc minutes for the globe. Time of occlusion for the observer was 55 arc minutes. Their standard refraction conditions put it up to 55 arc minutes as well. So pretty close there if you account for the thing that doesn't work for them. But then when you remove that, they're going to be off by, spoiler alert, it's 2 arc minutes again. So when we look at Cheyenne Mountain, which I think, did I just copy paste that? No. Okay, so 186 meters in lift for that 18 arc minute correction for celestial refraction. That cancels out their drop over distance there of 142 meters of drop over distance. And then the actual refraction difference at the time of occlusion was 5 arc minutes, coming out to 65 meters. And that does not exceed the 142 drop over distance, so we're good there, valid measurement. And the actual overcompensation created by this formula compensates by 165 meters for 142 meters of drop. So completely overcompensated. So if we recall back to super early on in this conversation, Mike was putting up the graphs and everything showing how the globe always overcompensates for refraction and then it underpredicts for the actual occlusions. This has been known for a super long time, but the things that we've been dealing with in the argumentation and the rigmarole, it's like we're just now kind of playing catch up and showing it in a way that might be a little more easier to understand. But this has always been in the data. This isn't anything like crazy or whatever. This is just re-illustrating what's already been there and the differences that have always been there the whole time. Matching the original graphs of globe under predicting and over predicting for the correction. We're seeing it every time we scroll down. Another one, Blodgett Peak. Look, they're going to be off by 3 arc minutes now because they don't have, so they're under and over for the correction. It's insane. Every time. So we have the drop over distance here giving us 101 meters for Blodgett Peak, 49 meters in lift. Actually, I think I did Blodgett Peak already. We're on Cheyenne Mountain now. Sorry, so 1.5 for the drop over, or for the rise over run to the peak. 11 arc minutes of drop, which creates 53 arc minutes for the globe. And no, I just did Cheyenne, didn't I? I scrolled up too far. Yeah, I did. So we were on Cheyenne. So just off again by the 2 arc minutes because we removed their ability to have terrestrial refraction. And then looking at what they compensated for the drop over distance, 142 meters for drop over distance, compensated by 165. Classic. Blue Mountain, same situation. We have 1 degree, 4 arc minutes for the rise over run, minus 13 arc minutes for drop over distance, giving us a clean 50 arc minutes for the globe, 52 with terrestrial refraction. Time of occlusion puts the apparent position at 252 for the observer, at 52 for the observer, with a cool 19 arc minute refraction correction. The actual separation at the time of occlusion was 3 arc minutes, and That gives a difference of 16 for their astronomical refraction, giving us an overcompensation of 16. And when we look at how that affected the measurements, keep in mind 200 meters in drop over distance, essentially. And they overcompensated by 218. The actual measured difference was 54 meters, and they predicted 273 in lift. So they lifted up 273, predicted 200 in drop. Valid measurement, though, as the measured amount did not exceed the drop over distance, so we're good there. And they're off again by 2 arc minutes. Now we have the most interesting case here because we have the lowest amount of astronomical refraction ever recorded, and we have the amount of terrestrial refraction, converting the 2 pi r, 7/6 into meters or degrees per meter. So we know that the terrestrial refraction would have had to have been at least 2 arc minutes here. And this measurement has an angular separation from the peak of only 30 arc seconds, which is extremely small. So rise over run to the peak gives us 1 degree, 43 arc minutes. For the globe, they predict 12 arc minutes of drop, giving them 131, or giving them 130. Refraction gives them 132. Time of occlusion with respect to the observer is 132. And that's adding their 15 arc minutes of refraction. So to see how that affected everything, we're going to go down now. 178 meters of drop over distance. The refraction correction netted them 215 in lift. The actual measured difference was 7 meters because it was only 30 arc seconds. So it comes out to 7 meters difference. So we were only 7 meters off the prediction here. The astronomical overcompensation factor due to this is the full 15, essentially, because if you subtract what that was from the arc seconds, it doesn't even drop it to 14. Anyway, so they predicted 200. That leaves them with 208 meters of overcompensation. Green Mountain, then again they were off by 2 arc minutes for the visual. And then for Green Mountain, we have 1 degree, 6 arc minutes. And then for the globe, they want 14 arc minutes in drop, giving them 51 arc minutes for their prediction, 53 with refraction. Apparent position of the star was at 1 degree. So they're actually off by like 7 arc minutes here. The star should have been above it when you add the terrestrial refraction in. So they have 24 arc minutes of celestial or astronomical refraction there, giving a difference of the actual angular separation was 1 arc minute, 9 arc seconds, which comes out to a 22 arc minute difference between their predicted amount, their empirically derived amount at the location for Mount Rosa. And then that comes out to be 200. So their drop over distance for that 14 arc minutes was 217 meters. The refraction correction gives them 366 meters in lift. The actual separation at time of occlusion was 18 meters. The overcompensation factor by their 22-minute refraction difference is 348 meters. But again, the drop over distance did not exceed the measured amount, so we're good. Still valid. And here they're off by 9 arc minutes. That's a catastrophe. North Peak. Rise over run gives us 45 arc minutes to the peak. Subtracting 35 arc minutes for the drop over distance gives us 9 arc minutes. With terrestrial refraction, they predict 14. Time of occlusion was 11 arc minutes. So here they're off again. The star's true position was minus 12 arc minutes. The 360 times the distance prediction was off here by 26 arc minutes. And this one. Okay, so when we get into the flat Earth prediction here, the star was the true position separation was at 58 arc minutes relative to our 45 predicted with the rise over run to the true elevation of the peak, which creates a minus 13 separation there, or negative 13 arc minutes. I have arc seconds listed here, so I need to change that, but that's arc minutes. So that creates a difference of 36 arc minutes. So that'll be cool to see how that affects the measurements. When we go into the drop over distance, there's 1,340 meters of drop over distance. The Bennett correction gives them, that can't be right. That's North Peak. Yeah. Their drop over their celestial lift from their astronomical refraction gives them 886 meters for their lift relative to their drop over distance, and then the amount actually measured because of the difference being higher than what we predicted comes out to be minus 560 meters. So valid measurement, they did not exceed the amount, or our measured amount didn't exceed the drop over distance there, so we're valid in that. But we see with the actual amount of refraction there, because there was 13 arc minutes of refraction of actual angular separation between the two, and we see how that affected the measurements there now, and why it was off, right? Because so the true position of the peak had to overcome 12 arc minutes of change there, and that affected the measurement pretty wildly. So now the elevation that we predict is off by 500 meters, which isn't the worst. But then when we get to the distance part of it now, we're off by 30,000 meters. So the reason that changed is because the ratio of the triangle in relation to the one that created the 145 is now completely different, because the separation that occurred of 12 arc minutes is like affected it too much. Because if it's like 2, 3, 4 arc minutes, it's still going to be within like pretty close. And we'll see that as we continue on. But once we start to get into 8, 10, 12 refract, like that's when the angle relative to what we predict has changed so much that it's not going to be possible for us to derive a distance that's close to what it actually was based off of that angle, because it no longer bears any relationship to what derived the original angle in the first place. So it's a cool, interesting way to quantify that. Okay. So let's see here. So I think we went over everything for that. So yeah, and now in terms of apparent, so for their apparent position, they're now off by 2 arc minutes. So simply going here and looking to the peak at the time of occlusion is not going to work here. They predict that they predict the refracted peak is even higher than the apparent. So they're untenable. Getaway Mountain. The rise over run gives us 53 arc minutes for flat Earth, minus 13 arc minutes for drop over distance for the globe, giving us 39 arc minutes for the globe prediction. Standard refraction lifting us up to 41. Apparent position with respect to the observer was 14. I'm just saying random numbers here. 42 arc minutes, and the astronomical refraction amount is 23 arc minutes. So when we come down to the separation with respect to the peak here, we have 45 arc minutes, and then we have that creates a 7 arc minute separation, which gives us a difference from their prediction for refraction by 16 arc minutes. When we look at how that affects the measurements here, we have minute refraction giving us 333 meters of lift to compensate for a drop of 178 meters. The actual measured difference with that, what was it, 7 arc minute difference? So with this 7 arc minute difference, it comes out to be 140 meters of difference. And their overcompensation factor there was 230 meters. Pretty insane. And so real quick to look at that. Something I want.
Wait, where's all the concave evidence? I keep hearing this guy tell me that this produces concave results. I haven't seen any yet, though. Could you find some for me?
Yeah, I can find it. So if you go to the simulator made by a guy, it has a quadratic refraction formula put in it that's applying the astronomical refraction.
Oh.
And so when you go to a certain distance, that inverts because it's hyperbolic. So when you overextend on that, it's an artifact of the simulator. It's not reality. So
wait, so that sounds like it has nothing to do with this, but because some guy made a simulator that you can push past its threshold with a scale sliding bar, that somehow would invalidate the method. That's confusing, though. Why would somebody say that?
Because they don't actually have a real argument. That would be my guess.
Oh, I get it. Okay, all right.
That would be what I would assume. Awesome. Okay, so as we continue here now, they're off by 3 arc minutes for their apparent position shenanigans, which completely untenable. Houndstooth, now we have our largest angle here, but also shortest distance. So 10 degrees, 39 arc minutes. The globe predicts 2 minutes of drop, which gives them 10 degrees, 37 with refraction. Star's apparent position at time of occlusion was 10 degrees, 36 arc minutes. The amount of astronomical refraction prescribed by Bennett is 4 arc minutes. And now this one's really cool because there's 1,600 meters for, that's for the elevation, sorry. 8,804 meters is like 5.4 miles. So this was the shortest distance one with 4 meters of drop over distance. That's hilarious. So anyway, when we look at the figures here, we have time of occlusion with respect to the peak, 1037. 4 arc minutes was their refraction applied there. 2 arc minutes of difference in separation there. They overcompensated by 2 arc minutes. The refraction boost gave them 10 meters in lift. They predicted 6 meters in drop. The difference was actually 5. They overcompensated by 5. And they were off by 2 on the apparent. So even in the, even at this distance, it's untenable for them to, hinging it all on Pikes Peak was such a mistake because it's like one of the only places where it lines up so closely. And then everywhere out from there, it's just like, nope. All right. So old Blinn Mountain here. So this is Jesse's measurement. Giving rise over run to the peak gives 1 degree, 34 arc minutes, giving a minus 6 arc minutes for the globe, giving 1 degree, 28 arc minutes for their final prediction there, 129 with the terrestrial refraction, which isn't accounted for. And the star's position was at 130 apparent. Oh no, they exceeded their occlusion. Fuck. Sucks. I was hoping they could get 1. All right, so now we have the rise over run to the peak for flat Earth, 1 degree 34. The actual occlusion time was 121. The apparent position was with respect to the peak. Oh, no, never mind, not relevant necessarily. The peak, the astronomical refraction at that location was 20 arc minutes per Bennett's formula, giving a 12 arc minute of separation between the peak and the predicted refraction, overcompensating by 7 arc minutes. So the distance here was 22,000 meters. So this converts to 38 meters of drop, astronomical refraction compensating by 131 meters. And here we have the first case of the measured astronomical refraction amount exceeding the predicted drop over distance. Now this invalidates the measurement because how can it be said that the Earth is a globe if the amount of refraction had to cancel out the amount of drop over distance that would make the star intersect at a lower angle? And actually I say intersect here, but Blinn Mountain were occlusions. Now this is particularly interesting because we now have the reverse scenario of the 1-to-1 lift, where the star's true position is below the peak, so to speak, but it's being lifted up. Well, in this case, the star's true position is below the peak, but it's already lifted up. So when the star's true position and the peak intersect, it should immediately become visible per their premise and basis of how they're interpreting this 1-to-1 ratio of refraction. But what actually happens is the star had to get within 7 arc minutes of the peak before it was visible. So that fully substantiates our position that refraction isn't lifting things up 1-to-1 in the way that it's required for them to have their belief system. And that the methodology of analyzing the occlusion angle with respect to the peak, the thing that did the actual occlusion, is completely valid. Because otherwise we wouldn't know that the star's true position was only 7 arc minutes different than the peak, not 19 arc minutes. So if they predict 19 arc minutes of lift, and the star is at, for the observer, let's see, for the observer here, true position observer. So they would predict that that when the star is at 1 degree and 10 arc minutes, that this is now going to be lifted above it. But that's not what happened. the starlight had to wait for some reason. It couldn't get over the peak until the actual true position was within 7 arc minutes of the predicted drop over distance for the peak. And then so that's anyway fully substantiates our position, and the one measurement where it intersected with the globe, with what they would predict for the angle to the peak, was entirely facilitated by the refraction offset. So when we I kind of came up with like some error bars for some of the measurements about a month ago when we were going through that, and it was like, okay, so if you derive an elevation in a distance, if you're off by 60 meters in elevation, if you're not better than 60 meters than the other prediction, then they're indistinguishable. And if they're not better than 1,609 meters, which is a mile, then they're indistinguishable. And in the cases of Blend Mountain here, what we run into is instances where they're indistinguishable for some stars because this was a hill, and every star occlusion has a custom elevation change to account for where it intersected with the hill at the lowest point. These all change. So sometimes we're indistinguishable, and sometimes the globe is a little closer, but that's entirely facilitated by the actual refraction difference that had to come in, that came into a play that's offsetting it. So in the scenario at the same peak with different stars intersecting at different elevations, the same peak is giving globe or giving indistinguishable results, and then also instances where the result is better than what the flat Earth predicts, but only because the refraction difference here is completely overcompensated. The actual refraction amount, not the predicted fake amount that they are overshooting for, but the actual amount. So they predicted 38 meters of drop. The actual refraction there was 38 meters. And keep in mind, my man made a simulator to go and find these conditions explicitly to where they would line up. So it's really interesting that that amount of actual refraction existed there to facilitate the conditions to mimic the globe. That's hilarious. And when we look at same situation here for this peak, so this one was close on the distances and elevations here. But when we look at the same peak from a further distance, this first star, we're off by 10,000. And then on the next one, we're off by 15,000. So we increased a 5,000 difference there. But what happened? Well, the star's true position with respect to the peak is 42 arc minutes. That's what causes that's where it had to be before it emerged. Now, with 53 arc minutes for the rise over run for the physical elevation there, we're off a little bit. So, well, why are we off? Well, the star emerged when it was 10 arc minutes with respect to the peak. 10 arc minutes difference. It did, because of the refractive conditions, it didn't have to get closer, which affects the actual conditions affected it such that that's why we're off. And then on top of that, when you take this amount here, so it occluded at 42 arc minutes, right? Now, same mountain peak, same distance, but changing the elevation of the occlusion angle is now 38. Now we're off by that 5,000, but there was 14 arc minutes of refraction that caused that lingering. So that separation from our actual position. So as this angle gets lower because it's lingering in the sky longer, our ability to use a trig function based off of the rise over run to the original angle that created it is, becomes nil. So this is why the measurements get skewed in that way and why they don't work out, because the amount of actual refraction is compensating for it. And here, because the globe is already lower on on their prediction, they're actually able to maintain a decent distance prediction, and that's what saves them in the end. Because ultimately, they're always going to be off by what they predict for drop over distance to the elevation of the peak. So they predict 131 in drop over distance, but they're 131 off on the peak. Now we're off by 172, but there was 14 arc minutes of refraction. And what do you know, when you convert 14 arc minutes of the separation between us and the peak, comes out to 172. So we were actually dead off by the amount of refraction there on what would have otherwise been a flawless decapitation or whatever, flawless victory. All right, so 2 minutes off on. Oh, actually, that's the wrong peak. We're on these ones, the Ebens. So 6 arc minutes. No, I'm sorry. There are 4 arc minutes. Wrong one. All right. So for the one that we went over on the first one, this 663 star. No, that's 3 cap. For 663, they were off by 4 arc minutes on their apparent position for the intersection for the emergence. And then looking at the ratio here, so they predicted, what was it? No, that's not right. Got the figures wrong. Okay, so for starting from this one, so they predicted 131 drop over distance. There's 130 meters of actual refraction created by the 10 arc minutes of separation there. So we're within 2 meters of one another, like basically indistinguishable. Like even though it technically doesn't exceed it by 1, it's too close to tell. And then the other cases, 171 meters of refraction. They predicted 132 in drop, so they're outside of the confines of a legitimate measurement. Same here with the other ones when they were closer to Blinn Mountain. 84 meters in actual refraction, predicted drop over distance, 38. Same situation, 82 in actual difference, 38 in drop. So if you can't distinguish the difference in outcome, then it doesn't refute the null hypothesis. And the whole purpose of this, remember, is to refute the null hypothesis. It's not to to go, oh, look, it's indistinguishable, I can't tell, or whatever, therefore it doesn't work. That's absurd. All right, so that's where we're at with the analysis. Oh, we got one more. This is Goose's Mountain. This is Regulus being occluded at 4 degrees, 51 arc minutes for the prediction to the peak. And then we have a geometric drop of 4.5 arc minutes, giving an angle of 4 degrees, 46 arc minutes, 4 degrees, 48 arc minutes where the star was when it was occluded for the observer. So we'll take a look at where that was with respect to the peak now, and then we'll compare and contrast. So we predict 4 degrees, 51 for the peak with rise over run. The star was occluded at 4 degrees, 47 arc minutes. They predicted 10 arc minutes of astronomical refraction. There was an actual difference between the star's true position and the peak of 4 arc minutes, giving a 6 arc minute overcompensation. What that looks like: 21 meters in drop over distance, 50 meters in lift, measured difference of 20 meters. Oh, that's actually pretty close too. I didn't even realize that. So yeah, this one would be another case where it's in not valid. The difference there isn't, even though it goes our way, it's still not far enough, sir. So anyway, actual refraction conditions dictated that basically fully compensated. So this one would go either way when you look at the elevations here. So we derive an elevation. Let's see. Let's do a quick comparison before we wrap up. So we're off by 20 meters. That was the 4 arc minutes of separation, giving us 20 meters there for the angle. And then distance-wise, we're off by 235 meters. They're off by 22 meters for their drop over distance, so identical on that. And then for their distance, they're at 260. Yeah, they're basically identical. So yeah, that's another instance where where this wouldn't constitute as a measurement that's able to determine if the Earth is flat or if it's a globe. All right, any questions?
So refraction saves us. Excellent. We should try refraction all the time.
Dude, it not only saved us, but it destroyed them.
So what that really shows is that it's a post-diction and ad hoc that just is a factor they throw in to any situation that could bring it back from anything, right? So it's never real conditions. It's just, well, what does it need to be back to the globe? That's how much refraction there is. Oh, look at that. Crazy.
Yep. Yeah, that's where we're at with it, and I think the argument has pretty much reached its final form. This is there's no coming back from this.
Well, what if I endlessly obfuscate and deflect and never addressed any of what you just said? Aha! Then we can continue.
Oh, well, that's just called par for the course. That's not doesn't do anything.
You underestimate bring up refraction.
Yeah. Yep. All right. So I think that's everything. If there's no questions, comments, or concerns, we can wrap up for the night.
I'm a
was
little
super in-depth.
thirsty. Might need to go make a pot of coffee or something.
Oh, I had Lily. Would you put a pot of coffee on for us? Would you put some brush tail on? Hi guys, it's me, Lily. I'm here to put brush tail coffee on.
Oh God, I'm so sorry. I had to reopen the gadget. What do you call these things? The device.
Yeah, the thingy-majigger. Yep.
Coffee. I'll go make a pot of it right now, folks. Don't forget to buy the yummy brushtail coffee. Check out their menu. Some really tasty ones on there. Yep.
What's your favorite flavor, Lily? Mine's the Ethiopian blend because it's an earthy taste and it has a sweet hint of caramel in it. I don't know if it does or not. I've never had it.
You know, lately I've been really enjoying the one from Mexico. Yeah.
Oh yeah, the Mexican coffee. Yep.
And then also the one from Belize. I think it was Belize.
Yeah.
Or was it the Honduras? I forget. I don't know. I have to look at his catalog again. But
so Lily, last time you brought up the coffee, you mentioned that you were getting married. There were a bunch of men proposing to you.
Oh yeah, that's the other drawback. I mean, if you look at it as a drawback, is guys everywhere you go, they're like, "Would you marry me, please? Would you marry me, please?"
All right. Well, thank you, Lily. We'll go ahead and wrap up for the night. Let me take a look at the chat here. Shout out to the lads. Shalom, Cody, Nominal, Big Pine Sailing, Nominal, Flat Earth Daily. Think for yourself. Nightbot. Shout out to my boy spamming in the chat for me, holding it down in the streets. And Bogan. All right. We'll see you guys next week. We'll come back on Friday for the Twitter community space. Shouldn't have anything going on this week. So we'll should be able to attend that. And then we'll be back on Sunday where Man of Stone is going to be presenting on the Felix Baumgartner, Peace Be Upon Him, high altitude jump from the stratosphere or whatever it was. And let's see, what else are we doing? Oh, tonight at 10, join us on Discord or on YouTube. Stone's going to premiere his new 8-minute video, little expose on the Dr. Shiva guy, who was supposed to be getting involved with Flat Earth, doing some experiment or something, and apparently he's gone radio silence. So Stone's going to give us an update on that, and so stay tuned for that. We'll be back at 10 tonight. We'll be back at 8 on Friday, and 3 on Sunday, and then we'll be back again on Monday for Celestial Theodolite update number 20, and then we'll be back again for Aether Cosmology 101. Oh, quick announcement. Totally forgot to put this at the beginning. So we're coming up on our 2-year anniversary. That's going to be Aether Roundtable 104. Now, it's a couple weeks out. So what I would like, or what would be cool, is if everyone who's been watching, following along, if you've learned something from these presentations, anything at all, doesn't matter what it is, or if you've learned something new yourself and you want to share it, send in a little clip of you doing a presentation on it. 2-minute clips would be preferable, but you can go as long as you want, honestly. And we're gonna do a big watch party. We're gonna watch all the clips that are submitted in, and also I'm gonna be reviewing some of the old roundtables and some of the guest speakers and stuff that we're on, and go over some of the stuff that I learned and some of the big highlights and stuff. So it'll be a nice community recap of sharing and learning of what we've done the last 2 years. So if you haven't done any presentations, you've never done one, but you thought about it, you like the concept of what we're doing here, but you don't have the ability to financially support us or whatever, totally cool. Send in a video of you going over something that you learned from us, or something that you learned yourself that was inspired by, what we're doing here. And then we will play it and review it for episode 104. We'll do a big community showcase.
That's going to be awesome. And I don't want to socially shame you to force you to participate, but I might. And I don't want to name names, but I will. And I don't want to. It's really awkward, but I might get to that point. So it's going to be fun.
There's a lot of things I don't want to do.
How about if we give out a T-shirt and a hat randomly to, like one T-shirt and one hat picked from everybody who submits videos.
Ooh.
So if you submit a video, you'll be in the drawing for a hat or a T-shirt.
Nice. I like that. That's awesome. What Kat just said is the new thing also added onto it.
Yeah, man, that's going to be super fun. Community participation. Yeah,
it was an awesome shower thought, and I was like, "Ooh, we have to do that. That sounds awesome."
Is that where it came from? Shower thought? Nice.
Yep. All right, cool. So we'll see you guys throughout the week. Now, to submit the videos or whatever, you can email me at AlanSpaceAudits@gmail.com. There's a website called transfernow.com. You can use that to send me a link to the file, or you could upload it on YouTube, private it, and then send me that link, and then I can go from there. Or you could, however you want to send it, you can do that. Or if you want to send in like a PowerPoint or like some notes you took, like just like anything you want to do.
Literally any format that you choose is fine. Yeah.
Whatever is easiest and awesome for you. Even if you just want to write like, hey, this is, I like watching and this is the thing that helped me understand the blah, blah, blah. Even if it's like a testimonial, send it in. We'll go over it, present it. We'll add some graphics to it. It'll be awesome. All right. See you guys throughout the week and later tonight. Bye.